This is grade 12 physics, and we're going to be talking about work, energy, and power. Right, this is a section that a lot of the students that I've taught over the last years, they seem to have had a problem with it because I think you once again here you have to be one with the thing, and you have to say what's actually happening here and make some deductive logic because it actually helps. It's easier to understand it as opposed to looking for a formula and plugging it in, okay? Yes, we're going to do the recipes as usual, but first of all, let's just look at these terms, okay? And we're starting off with the changing back to my starting color, always black, work. Remember, work done was measured in joules, correct? And work done was force times displacement, which is meters. Force is in newtons. Newton meters. Newton itself is mass times acceleration times meters, okay? All right, let me just write that. That's Newton meters, all right? Now I'm going to change this and I'm going to say, right, the Newton is measured in what? The Newton is measured in kilograms, mass, times meters per second squared, which times meters is equal to kilograms, meters per second, all squared, correct? That's basically what we've got for work done. Now I want to look at energy, all right? All I want to look at initially is kinetic energy. Let's look at EK. Kinetic energy, or as I like to use, EK is equal to a half times m times v squared, correct? And mv squared is equal to a half times, now let's look at the units. Mass, kilograms, v squared, meters per second squared, which is a half, doesn't really affect us, kilogram, meters squared, per second squared, which means that we've showed that the work done is equal to the EK energy, correct? Now, let's just stop at that point, right? Let's just stop and think a second. If we are pedaling along, and if we want to accelerate, what do? Sometimes we have to get out the saddle, but you push harder. You exert a force. Remember, when we're pedaling along, the force we're exerting is equal to the drag if we're going at constant velocity, right? If I increase my force, and that force is greater than the force of friction on me, then I have got an F net. Remember in the previous sections, when we've got a body undergoing something, we look to find F net. Is there an F net anywhere? If there's an F net, immediately F net equals MA. Okay? So we need to just bear that in mind, that we're going to be looking at F net coming in now. Because if I'm going along the slope or upper slope or what I'm doing, and I am traveling at constant velocity, there's no F net. Because once again, going back to our graphs of motion, if you remember, there's no acceleration. V final, V initial are the same. Delta V over delta T is 0, therefore no acceleration. Now, let us have a look at a block on a straight or a horizontal surface, all right? Now, all I'm going to do is I'm going to put my block, I'm going to put it over here, okay? And I'm going to put a force exerting on that surface over there. Now, force at an angle, what did we do in previous things? We said, right, we have to split up into components. This is going to be opposite, so it's F sine theta. This is going to be F cos theta, correct? And now, let's have a look here and we say, okay, which is the force doing the work? Work done is force times distance. This block is not going up or down. it is only going to the left or to the right, right? That means F sine theta is less than the weight of the block pulling it down. Okay, so what happens now? It means that, therefore, I can say F cos theta, work done. Let me go back to my correct one. The work done on the block is equal to F cos theta times delta x, where delta x is the horizontal distance that I have moved the block, right? Well, now, in the textbooks, a lot of them, they say to you, yes, you've got the F cos theta, etc. We've now got to make a judgment call, because what if our force was over here like this, right? Now, theta is over there, right? What does it actually mean? Well, you and I would say, okay, it's either going to the right or it's going to the left. We'd logic it out, okay? But mathematically, we have to have our formula correct. So what we're saying is that F cos theta times delta x that way. But here, what is this one over here? Okay, this is going to be F cos theta as well, isn't it? Therefore, in this case, theta over here is going to be, cos of that theta is going to be negative. So therefore, we can have negative work or positive work done. Right? F cos theta can be positive, F cos theta can be negative. All right? If you like, let's say the block is moving this way, we've got a force acting the opposite way, right? So here's our block, and we're moving along this way, and the force is acting this way. It is actually removing energy from the block, isn't it? Let's just think about it logically. Let's not try and do it mathematically right at the moment. If I'm moving along and I hit a rough patch, I slow down. The energy is taken from me. My kinetic energy is reduced. Therefore, I slow down. Therefore, there's an F net that way, right? So, F cos theta, all you have to do is, if it's going to the right in this case, all right, it's in quadrant 1, it's positive. In quadrant 2, cos is negative. Therefore, that's quite straightforward. It's negative if cos theta is reversed. Now, let's just have a look. In your book, you've got conservative and non-conservative forces. That's just a straightforward section to go through. All right. I want to get to the nitty-gritty over here, because this is where it gets, or rather, this is where a lot of people have had a difficulty set. We've now got an object, a block on a slope. Right. Let's put block on slope. Here we go. What did we say when we have block on slope? It means the first thing we do when we have a block on the slope is we put in, we put in FG, FW, call it what you like, and then I've got, well, let me just put this over here, and remember our slope was theta. Then we said, okay, we put in that force, and we put theta up there. This is F sine theta, correct? Like so. And this one is going to be F cos theta, correct? Like so. Therefore, now, that's acting down the slope. F sine theta is acting down the slope, isn't it? But F G is actually equal to mg. So this is equal to mg sine theta. This is equal to mg cos theta, like that, correct? Mg sine theta, mg cos theta. Now, what is the next situation? The next situation we're going to look at is we're going to say, right, if that's the case, we transfer this force, remember, mg sine theta, we transfer that way, and we put our other normal force here is, whoops, sorry, we just put it as mg, and this is going to be our mg cos theta. That is F normal, isn't it? That is the reaction of the slope on the block, and the block on the slope. Right, so now we've put in our basic forces, correct? The next thing is we say, okay, obviously, which way is it moving? And we put in frictional force, let us say FF. The last, we've got an F applied. All right? Now you'll see this works for all cases. Whether it's going upslope, downslope, it doesn't matter. What we're doing is we're putting in F applied over there. All right? Now, I say the first thing I want to look at with you is I want to say, let us have a look at F net equals MA. F net equals MA. M mass times acceleration. That we know. Now, let's go back to my block. And I say, okay, this block moves up the slope to a position up there. So it moves delta x, a displacement up the slope or a displacement down the slope. It doesn't matter. All we're looking for is we're saying it's moving. All right? So you say, okay, what next? Well, if F net equals MA, if I now say, therefore, F net times delta x, in other words, the net force pulling me that way times the delta x must be equal to mass times acceleration times delta x, correct? I've just multiplied by delta x on that side. Now, this over here, let's just have a look. Mass times acceleration is equal to what? Times a displacement. Well, its mass is kilograms times meters per second squared times meters. Okay, delta x is meters. This is acceleration. This is delta x, and this is mass. Right? What does that give me? It gives us kilograms meters squared per second squared. Correct? But that is equal to kilograms times mass, meters per second times meters per second, which is mv squared, because each one of those is velocity. So essentially, the work done is equal to delta EK. The work done on the object is the change in the kinetic energy. Now let's just logic this out for a second. What did we say earlier? If I'm on a bicycle and I apply an extra force, right? That extra force is going to accelerate me. It's an F net, okay? Remember, the F net is the unbalanced force. It's the one that's causing the acceleration. So now I can go back and say, right, let us look up the slope. Up slope now. Up the slope, this is F applied. Look at your diagram. F applied, right? There. Okay, minus the force of friction, minus mg sine theta, must be equal to change in kinetic energy, delta EK. Correct? So but hold on, times the distance, okay? So delta x times that must be equal to change in, because this itself over here, this character is F net, isn't it? How would you find F net? You'd look which way it's unbalanced. If it's unbalanced going up, the force pulling up is bigger than the forces pulling down. Therefore, there's an unbalanced force up, and the unbalanced force up is F net. That's as simple as that. Similarly, if we're going to go down, we look if the unbalanced force is pulling me down. I'm going to accelerate down the slope, right? So my F net is the key here. And it's F applied, which is the force that's applied, minus the frictional force, minus the component of the weight down the slope or parallel to the slope, right? And that is equal to change in EK. Therefore, we can say that that is going to be equal to, let me just put it down, is going to be equal to a half mv final squared minus a half mv initial squared. Or if you like, a half mv final squared minus v initial squared, like that. All right? So very important that we see that. Okay? That gives us the along the slope, right? So if there's an acceleration, it's going to be caused by an F net, parallel to the slope. Now, let's go back to our slope. Okay, whoops, a bit too far. I just want to complete something here. Okay, it is on to black. So I just want to go along over there. Excuse me a second. I want to go here. And I want to say that is H. Okay, that is the vertical height. Whoops. Actually, my H is here. Sorry, I made a slight mistake over there, because on my drawing in my book, okay, that there is theta, isn't it? Okay, can you see the block has moved a height h from there to there? It's moved a vertical height h. H is the vertical height. Okay, it's the vertical height that the block has moved. All right, now let's just have a look at something. All right, you know that change in, now I'm going to look at potential energy. Potential energy, also EP, right? And it's equal to what? M times G times H. So change in EP is going to be equal to mg delta H, is it not? All right, correct? Now, let's just have a look at the triangle. Sine theta is equal to opposite over hypotenuse. Let's just go back. The sine of the angle, theta, stop there, and let's just put it onto red. The sine of this angle is opposite h over hypotenuse. So it's height there over the delta x, isn't it? Sine theta is equal to h over delta x. Okay? It's critical that you stay with me here, is equal to h over delta x. Right? Therefore, h is equal to delta x times sine of theta. All right? Now, change in potential energy, okay, is equal to, oops, okay, the change in potential energy is equal to mg sine theta times delta x, okay, which is force parallel times delta x, right? Because all I've done is I've said that is what I've put back into m, isn't it? mgh, but h is delta x sine theta, right? See that? I said potential energy is mg delta h, all right? And I said, let me just go back here. That is going to be equal to mg times delta x sine theta. Okay, that's delta h, isn't it? This here is being replaced by that. So therefore, mg sine theta delta x, correct? And mg sine theta is the force parallel to the slope, the weight parallel to the slope, right? F parallel. It's the component of the weight acting down the slope. It's equal to, let me just circle it in red. It's this force, right? So that force there, right, is in fact the one we're going to be using to work out our change in EP. We just go through it again. We say righty-ho. Here we've got mg delta x sine theta. I have rearranged it and made it mg sine theta times that. This is the force parallel to the slope. In fact, it's the weight acting down the slope times delta x is the change in EP. All right? And these are the two bits and pieces we're going to be looking at, EP and EK. All right? Now, in all these situations with the work energy theorem, it's really applicable to do the drawing, put in the weight components, solve them, and treat it like a force equation, right? Because when we start turning it around and coming down the slopes and so forth, there's an error that's going to occur in the cos theta element or the sine theta. But if you've actually physically done it, you've drawn your let's say your force diagram, that will give you the exact picture of what's happening. I know from experience from students that what everybody's trying to do is they're trying to get through it quickly, understandably so. But what they're trying to do is they're trying to apply formulas directly. You can't do it. You actually need to know which way they are going. Because if the block is moving down the slope, let's have a look at one moving down the slope, shall we? All right. Let's just take a block moving down the slope here. Just for the heck of it. All right. Here we go. And we've got a block over there. All right. And I'm going to do it. And let's say the block gets to there. And here's our slope of theta over there. And we say, right, let's put in our components. Like so. This one here is going to be F or mg, theta opposite, sine theta. So standard mg sine theta, correct? And in this case, you're going to have, that's going to be mg cos theta, mg cos theta. By now, we should all be very au fait with that. Red, in this case, this block is going down, therefore F is acting up. And on top of it, I say that I have gotten F applied this way. Because the block is accelerating down the slope. My truck is accelerating down the slope, right? So what happens now? You can see that here, my F net, let's have a look here. F net is what? Is equal to F applied plus mg sine theta minus FF. Right? So in all cases, you've got to just draw it because it makes it easier at the end of the day. Okay? Can you see there? The applied force is actually being added. Here. It's being added. So the F net is the two together. Why? Because the friction might be a big force. And I might need to put a little bit of accelerate or a little bit of energy into the equation to get myself down the slope. Who knows? Okay, we don't always end up freewheeling down a slope because it depends on FF. And yes, that is equal to MA, or that is equal to times delta X equal to my change in kinetic energy. Can you see why we actually do a drawing? I know, and believe you me, I have it all the time. You know, I haven't got time. I'm not in the mood. I don't feel like it. Why must I do it? Nobody else does it. Blah, blah, blah. The difference is, the reason for it is it makes it easier for you to actually work it out. Okay? The next bit I'm going to do is, I know I'm preaching. I do that a lot, don't I? What we're going to do is we're going to look at a couple of cases, all right, in this. We're going to go and we're going to say, right, case 1, case 2, etc., etc. We're going to go through those. Then we're going to do a couple of problems in the next one. I don't want to start bits and pieces because I don't want to sort of overrun to make it too long. Thanks for watching. Please draw them. As I say, the next section, we're going to come back, we're going to do cases. Cheers for the moment, and thanks for watching. Bye.